Welcome back to the deep dive. If you've ever looked at one of those huge global energy projections, the kind that guides billions in investment and shapes policy, and wondered, well, do they actually account for anything beyond just CO2 targets? Then this deep dive is definitely for you. We're going straight into the academic thinking here, trying to understand what really makes an energy plan sustainable.
Yeah, and for this, we're looking at a really comprehensive framework. It was developed back in 2018, published in a paper called Sustainability Guardrails for Energy Scenarios of the Global Energy Transition.
Okay, so sustainability guardrails sounds serious.
It is. You can think of this study like a highly specialized auditor. It reviewed a bunch of well-known energy scenarios, from places like the IEA,
Yeah,
Shell.
the big players.
Exactly. And it had one crucial mission, to figure out if these scenarios were genuinely sustainable or maybe just focused on being low carbon.
And the finding was pretty dramatic, wasn't it? That just focusing on CO2 is, well, dangerously incomplete.
That's the core argument, yes. This narrow focus, the paper argues, creates these massive blind spots. And that compromises not just the planet's ecosystems, but also, fundamental social justice issues.
Okay, so let's unpack how they tried to build a better framework. What was wrong with the old way?
Well, historically, energy scenario modeling has almost exclusively prioritized CO2 emissions. It's usually about hitting that 1.5 or 2 degree warming limit.
So the atmosphere was basically the only constraint people worried about.
Pretty much. But if you're planning the entire global energy system for the next 30 years, you really have to account for the whole planet, right? Not just the air.
That makes sense. And that brings in this idea of the planetary boundaries framework, doesn't it?
Precisely. For anyone listening who isn't familiar, this is the idea that there's a kind of safe operating space for humanity. It's defined by these hard biophysical limits we shouldn't cross, or we risk triggering irreversible changes.
Okay, so the authors took this bigger planetary boundary idea and applied it to energy scenarios.
Yes, and when they did that, looking at existing scenarios through this wider lens, they found several really critical environmental issues that were, frankly, often neglected.
So it's about broadening the definition of green beyond just carbon. What were some of these neglected boundaries energy planners were ignoring?
Well, the list is quite long, but some of the most critical ones include stress on biochemical flows, especially nitrogen and phosphorus cycles. Big ones.
Okay, nitrogen and phosphorus.
Yeah. And also significant land use change and, of course, biodiversity loss.
Right. So thinking about land use or maybe water stress,
Hmm.
does this study imply that things like massive bioenergy projects or maybe huge hydropower dams could look good on a CO2 spreadsheet,
Uh-huh.
but actually be unsustainable because they break these other ecological limits?
Exactly. That is the core critique right there. The study also points out we need to account for things like stratospheric ozone depletion, chemical pollution, freshwater use, and even atmospheric aerosol loading.
Wow, okay. That's a lot more comprehensive.
It is. And ignoring these other, let's call them 8 boundaries, means you haven't really defined the planet's true capacity to handle what we're doing. It's a necessary check, particularly now, given we're living in what scientists call the Anthropocene.
The age where humans are the main driver of planetary change.
Right. Our activities are shaping the planet itself, so we need these guardrails.
Hmm. That really sets the environmental foundation. But the critique in this 2018 paper went further, didn't it? It tackled the ethical and social dimensions too, which feels quite rare for this kind of modeling.
It absolutely does, and this is where many scenarios really sort of fell short. The study found that crucial ethical choices were often just not discussed or quantified or even justified in the models. They were basically hidden assumptions, not debated policy choices.
So if the environmental limits are non-negotiable, what are these hard limits set by society and ethics that need to be part of the picture?
We're talking about choices like ensuring access to preserved ecosystems, not just for us now, but for future generations too.
Intergenerational equity.
Yes. And also looking squarely at avoiding energy resource risks. That means minimizing conflicts over resources, extraction conflicts, and critically, avoiding the negative impacts that getting and using energy has on actual human lives.
Like local pollution, dangerous working conditions, maybe even the geopolitical instability that comes from relying on certain supplies.
Exactly. All of that falls under these socio-ethical guardrails.
I see. And this brings us to a key structural idea in the study, this hierarchical sustainability framework. It wasn't just a flat checklist of goals, was it?
No, not at all. The environmental dimension, those planetary boundaries we talked about, serves as the absolute foundation. The argument is you simply cannot achieve sustainable social or economic outcomes if you've already blown past the planet's ecological limits.
So environment first, the
Mm.
non-negotiable base.
Correct. Those environmental guardrails underpin everything else. Social and economic goals have to be built on top of that stable environmental foundation.
Okay. So looking at the models through this more rigorous lens, what was the most maybe surprising analytical failure they found, even in scenarios trying to be progressive?
It was actually a failure of, well, engineering analysis, you could say, a really fundamental one. All the global energy transition scenarios they investigated failed to properly describe the critical roles of flexibility and resilience in future energy systems.
Flexibility and resilience. Why is that specific oversight so important? And why was it missed so consistently?
Because if you're aiming for high shares of renewables like solar and wind, which are weather dependent, right? You absolutely need immense flexibility to manage that intermittent supply.
You need ways to balance things out when the sun isn't shining or the wind isn't blowing.
Exactly. And that means specific technologies. Large-scale energy storage, smarter grids, ways for demand to respond, managing the supply side cleverly, linking different sectors like heat and transport.
Okay, a whole suite of solutions.
Right. But here's the kicker. Not a single scenario they reviewed actually quantified the global demand for these flexibility components. So the models lacked a clear analytical description of how a highly renewable system would actually function reliably.
So they could calculate, say, how many solar panels we need,
Yeah.
but not adequately model how we'd keep the lights on reliably hour to hour with all that variable power.
That's the core of the problem. It's a serious methodological shortcoming. It kind of calls into question the technical viability presented in many models.
Wow. Okay, let's shift to the operational side then. How do specific technologies stack up against these stricter guardrails? Starting with efficiency, that seems key.
Efficiency gains, especially through electrification, are absolutely fundamental. The study argues they're key to cutting primary energy use overall. Take vehicles, for instance.
Okay.
A battery electric vehicle, a BEV, running on renewable electricity. It's about 3 times more efficient than a comparable diesel vehicle, and maybe 4 times more efficient than a petrol one.
That's a huge distance, just baked into the technology shift itself.
Massive energy savings, yeah. And you see similar things in heating.
Heat pumps, I imagine.
Absolutely. Electric heat pumps are remarkably efficient. We're talking 4.5 to 5.5 times the efficiency of just burning gas or oil directly for heat. So wherever you can swap combustion for electricity powered renewably, you dramatically lower the total energy demand.
But efficiency isn't just about the tech, is it? The study flagged a major social hurdle, using an IEA analysis of Nordic countries as an example.
That's right. To hit deep decarbonization targets, that IEA analysis found they'd need an annual building renovation rate of something like 2 to 3%, upgrading insulation, windows, heating systems.
2 to 3% per year. What's the reality?
The reality at the time was closer to 0.5% per year.
Oof, that's a huge gap.
It really highlights a severe social sustainability challenge. You can set ambitious targets, but unless you account for the public consultation, the stakeholder buy-in, the policies needed to actually get people to undertake potentially disruptive renovations on that scale, the target might just be unrealistic.
So the social acceptance and feasibility of the transition are just as critical as the physics or the engineering.
Exactly. It's all interconnected.
Okay, let's tackle some of the high-risk options now. We talked about the ethical guardrails, especially the intergenerational ones. How does something like nuclear power, which is low carbon, fare against that specific criterion?
Well, according to this study's framework, nuclear immediately runs into trouble with the intergenerational ethical test, primarily because of the long-term nuclear waste issue. We're talking thousands of years of management.
A burden on future generations.
Yes. And then there's the risk profile. It's unique.
Yeah.
The sheer scale and potential consequence of accidents carry this enormous risk, which most models tend to treat as an externality, something kind of off the books.
And the study actually put some numbers on that risk, didn't it? Figures you don't usually see in simple cost comparisons like LCOE, levelized cost of electricity.
It did. It cited data covering 1950 right through to 2014. It detailed 686 global nuclear safety incidents, and the estimated human cost was stark. Around 182,794 deaths attributed to those incidents.
Wow, nearly 183,000 deaths. That's staggering.
It is, and the estimated property damage was around $265 billion. These are massive real costs, but they're rarely integrated into the kind of comprehensive risk assessment this study is calling for.
And financially, even putting aside the accident risk, nuclear often struggles on cost alone now, right? Compared to renewables.
That's another key point. The study mentioned the estimated LCOE for Hinkley Point C in the UK at around €113 per MWh, which frankly just isn't competitive with where solar PV prices were heading even in 2018, let alone now.
And this cost disadvantage is especially striking when you consider the history of public R&D funding.
Exactly. The study tracked cumulative public energy R&D spending in OECD countries from 1974 to 2014. Almost half, 48%, went to nuclear energy,
48%. Compared to what for renewables?
compared to just 11% for all renewables combined over that same period.
So 4 times more public R&D money historically poured into nuclear than renewables, and yet nuclear is often still more expensive than solar PV.
That's what the data suggests. It really reframes the cost argument against nuclear power, especially when viewed through the sustainability lens.
And that tilted playing field doesn't even account for the massive subsidies still propping up fossil fuels, which distorts the baseline even further.
Absolutely correct. The study cited an IMF finding that total fossil fuel subsidies, and this includes the hidden costs, like damage from air pollution, health impacts, even military spending to secure supply lines.
The stuff usually left out of the price tag.
Right. Those subsidies amounted to something like 6.5% of global GDP back in 2015. It just confirms that many energy scenarios operate with unrealistic, artificially low baseline costs for fossil fuels.
Okay, now let's talk about carbon capture and storage, CCS. This technology often shows up as pretty indispensable in scenarios from groups like the IEA. Did this 2018 study agree?
They expressed, let's say, deep skepticism about its necessity and viability.
Why skepticism?
They argued that the perceived necessity of CCS is often based on scenarios that used outdated, overly high-cost assumptions for alternatives like solar PV and battery storage. Basically, renewables got cheaper much faster than many models predicted.
So the need for CCS might be overestimated if you use up-to-date costs for renewables and storage.
That's the argument. Plus, CCS itself faces significant constraints according to the study. Storage capacity underground isn't infinite and can be geographically limited. The costs remain stubbornly high. There are real risks of leakage, which could undermine the whole climate goal.
And it doesn't really offer other benefits, does it? Like cleaning up local air pollution.
Exactly. It offers no ancillary benefits. It just deals with the CO2, assuming it works perfectly and stays stored forever. It doesn't tackle other pollutants or improve energy access or create the same kind of distributed jobs that renewables can.
So if it's expensive, risky, potentially unnecessary based on updated tech costs, why does it feature so prominently in mainstream modeling? That kind of brings us back to transparency, doesn't it?
It really does. And transparency was another major focus for the authors. They actually applied a specific transparency checklist to the 8 major global scenarios they reviewed.
A scenario scorecard, essentially. What did that reveal about how open these big organizations were about their methods and assumptions?
Well, the results were pretty varied. The study noted that IIS's Global Energy Assessment, the GEA, actually scored the highest on transparency.
Okay, so some were better than others, but were there common weaknesses?
Oh, definitely. Common weaknesses were clear across the board. Most scenarios failed to fully disclose their detailed cost assumptions, and crucially, many did not disclose their funding source.
Not saying who paid for the study. That seems basic.
You'd think so. But not disclosing who commissioned the research makes it incredibly difficult for policymakers, and for you, the public, to assess potential biases or vested interests that might be baked into the model's assumptions or conclusions. It's a significant ethical gap.
A huge one. Okay, so we have issues with neglected boundaries, ethical blind spots, transparency. But what did the study identify as the single most severe methodological flaw found across all the scenarios they looked at?
We touched on it earlier, but it bears repeating because it was universal. No single scenario they reviewed had quantified the demand for energy storage capacities on a global level.
Still circles back to that flexibility issue.
Exactly. Which means, as we discussed, that these scenarios, especially the ones projecting very high shares of variable renewables like wind and solar, fundamentally lack a clear analytical description of the flexibility the system needs to actually operate reliably.
They haven't modeled how to keep the grid stable hour by hour, day by day with all that intermittent power.
In essence, yes. They might look technically feasible on an annual energy balance sheet, but their operational viability, their hour-to-hour functionality, is analytically underdescribed, or even undescribed in some cases.
So after applying this really tough, comprehensive set of guardrails, environmental, socioeconomic, ethical, transparency, technical feasibility, what kind of energy pathway did the study conclude was the most robust and genuinely sustainable?
The study's conclusion on this was quite clear and direct. It found that scenarios aiming for a fully renewable energy system, the kind modeled by organizations like Greenpeace or WWS Solutions Project, are the ones that fulfill this comprehensive set of sustainability objectives most effectively.
So 100% renewable pathways came out on top when judged against this full suite of guardrails.
That was their finding, yes. They argued these pathways perform best across the environmental, socioeconomic, and ethical dimensions simultaneously.
This 2018 study really feels incredibly important then. It gives policymakers, and all of us really, a much more complete auditable framework for judging energy plans. It pushes beyond just simple CO2 targets.
It forces us to ask much tougher questions about environmental justice, about land use trade-offs, about the financial history of different technologies, about intergenerational risk.
So what's the final call to action from the paper? Where should we go from here?
The final call to action is quite direct. It argues that these fully renewable energy system scenarios shouldn't just be seen as niche alternatives. They should be regarded as real, viable policy options.
And maybe even the default.
Essentially, yes.
Yeah.
They should be set as the reference point. If any alternative scenario involving, say, large-scale nuclear or CCS is proposed, the onus should be on that scenario to demonstrate why it achieves all the sustainability objectives more comprehensively than a fully renewable option.
That really flips the script on how these things are usually debated.
It does.
Which brings us perfectly to our final provocative thought for you, the listener. This study strongly implies that applying this full range of guardrails, especially the ethical ones, about transparency and intergenerational equity, doesn't just make the science better. It also acts as a powerful filter.
A filter for what?
A filter that helps expose potentially self-serving assumptions or vested interests that might be hidden within the complex models shaping our future. So, the next time you encounter a major global energy projection looking out to 2050, maybe ask yourself a couple of questions based on this. Like, does this scenario actually quantify its flexibility needs, the storage, the grid upgrades, and maybe more fundamentally, what long-term, potentially expensive or dangerous risks did its authors implicitly accept on behalf of future generations without maybe making that explicit?
Those are absolutely necessary questions for navigating the path ahead. Critical questions.
That's it for this deep dive into the sustainability guardrails for energy scenarios of the global energy transition. Thanks for tuning in, and we'll catch you next time.